So this is right here, and today we're going to go over the lesson of 3.2, which is zeros of polynomials. We're going to go over part 1. So first we have to, it's going to be about 2 to 3 videos. First video is going to be about factoring. Factoring is large unit, large portion of zeros. And the second part is discards or possible zeros. So right now let's jump into factoring. So what's the definition of a zero? The definition of a zero is the value of x, which f of x equals 0. That's like you said. So right here, if x were to be negative 3, then this whole parentheses would equal 0. Meaning when it times this 0, times this 0, times this, everything is 0. So that results in f of x equals 0. So negative 3 works. What I want to focus on here is irrational and complex imaginary zeros. So why do these irrational zeros and complex imaginary zeros always come in pairs that look something like their opposite? Well, it's because they're conjugates. So if we've done exponential and radicals before last year, so let me show you why it's always in pairs. So to show you, we have to go to factoring. So right now we're going to use a difference of squares. So a squared minus b squared equals parentheses a minus b times parentheses a plus b. So that would, for this example, be 3x minus 4 times 3x plus 4. Let's just sort of memorize now. Just utilize this first. Just don't care about the others. And so this is, if you have to factor this, it would be x minus square root of 2, because what is for example b squared equals 2. What's b? B equals square root of 2. Except but we don't put the plus or minus here in this example because it's a rule that actually, yeah, you can add the plus or minus because guess what? B plus or minus equals 2. You're still gonna have plus or minus for this one, so it doesn't really matter. So the square root of 2 would be b, and so that would also result in this. So in order to get irrational zeros, they have to come in pairs, in conjugates, or else it can't, because their function most likely doesn't contain radicals in them. In fact, I think it can't. So that means all of this has to come in pairs. Let me give you another example. For example, it works the same way if I were to have x to the 4th minus not to this one, 3 equals f of x. So what would this be? This would be x squared minus square root of 3 and x squared plus square root of 3. Well, that wouldn't be in complete factor form, but that would give you a pretty basic idea of why you would have all these pairs. This, in fact, is not factor form, but it would give you a pretty good idea why they always come in pairs, because they have to come from a rational number, and because either a difference of 2 cubes, or difference of 2 squares, or some difference of 2 cubes. Because of that, it's going to transform into irrational zeros. So now we've covered rational zeros. What about complex imaginary? So it works the same way, actually. So there's not much difference. Using the formula, let's just write it down. A squared minus, I really love this formula. A plus B times A minus B. And so for this example, if we have f of x equals x squared plus 1, well, you might think, whoa, wait a second. It's plus 1. This is minus, and this is plus. That's different. But we can remember, complex numbers are really complex. So we can change that into negative and into 1. So this would become b, and this would become, sorry, this would b squared, and this would become, sorry, this would become a squared. So that would be a squared minus b squared. So that would work, except it would be complex. So right now it's a squared. So let's get a. So a is x plus. What's the square root of -1? I. So now you have the sort of thinking process when you try to get an imaginary root. So it's very hard to comprehend at first, because you look at it and you just skip over it because it's plus. But when the problem asks you to include complex imaginary zeros and irrational, you have to think hard and try to find the mistake, sort of. So x plus I, x minus I. So that's also why I always come in pairs, because you notice a pattern, because these are conjugates and these are complex conjugates. So it actually makes a lot of sense, because these are sort of not the integers or the rational numbers that we are used to. So meaning that to separate that, you sort of get two pairs. That makes sense. So it sort of makes sense to me, because for me I normally won't use irrational or complex imaginary zeros. So I sort of think of it as a separation, like half of a rational number. So that's complex, and should I leave this here? Okay, I should leave this here. And so we've gone over the definition of a zero and the value of x, f of x. So now let's go over factoring. Factoring. This is the chart. Can we just erase it? So I have to go over factoring before we can actually make it to factoring. So you can just look at this graph. It's very hard to digest in such a fast way, but I personally, so I don't think it's helpful to memorize this formula. I think in a way, it's, for me, I wouldn't memorize this. I would memorize the other way. I would memorize it as a plus b squared equals a squared plus 2ab plus b squared, and a minus b squared equals a squared minus 2ab plus b squared. I would memorize it like this instead of working on x, because many times you have to expand it, and expanding it, I think it develops more. So I'll teach you another way to sort of factor not just perfect square trinomials, but factorable trinomials. So I will substitute this into this, because I don't think this formula is actually really helpful, to be honest, because so you can just sort of quickly memorize this. Remember, common mistake would be this and this are different. This and this are different. So I just want to point that out first. So, for example, if it were to be 25x squared plus 30x plus 9, this is my old way. I don't think Mr. Hua taught this, but he didn't teach this. But I think last year when we were taught factoring by Mr. Huang, he taught us a different way. But I think this way it works better for me. But you can sort of get the other way. So the first thing you should do is you should put, if it's a even, no, not even, is a exponent of 2. So if the exponent is an exponent of 2, or basically if the exponent is a multiple of 2, basically if exponent is a multiple of 2, then normally, for example, 8. If you want to change 8 to x, because what you want. So another easy way to remember is what you want to put in these two sort of boxes is this. Is the in the middle of the triangle. So what you would, so we will use this later. So first you would prime factorize, because this is a perfect square, so it's definitely. So for prime factorizing, normally you would include ignore the 1, but I would like to include 1 in this purpose because many times factoring for my my method includes the 1 and the 25, or the 9 and the 1. So I'll make an example here. So I just wrote the answer first. You don't have to worry how I got that, but I'm gonna show you the thinking process of my. So what you want to try to solve is, it sounds complicated, but it's actually not. Plus sign. So what the arrow means is cross multiply. So in this case, 3 times 5x is 15x. And the plus sign means just add 2. And 5x times 3, which is 15x, which equals 30x. So the reason I found I got the numbers 5 and 5 instead of 125, 9, and 1 is because I sort of calculated in my brain that this would result in 30x. And why is it 30x? Because you have to equal the middle number. Well, many mistakes that students would make would be to do this method, or perfect square triangle, I don't care, but without doing common factoring first. So common factoring really reduces the amount of work you have to do, both my method and the original method. So after this, if it's correct, 3x matches that. And the next step you would do would be to have separation. So you would have, so remember, the plus sign is really significant. The plus is 5x plus 3. 5x plus 3. You would treat this as a set and treat this as a set, as a set of parentheses, and this would be equal. Would equal 5x plus 3 squared. That makes sense, correct? So there's just a little bit of problem because there's a plus sign. It doesn't necessarily mean that is always going to be add, because in some cases, remember, 9 prime factorization, we don't include plus or minus. So you could say it could be negative 3 and negative 3, but it would be negative 15, negative 15, or negative 30. But negative 30, so if this is negative 30, then of course it would be 5x minus 3 squared as the result. But this is positive 30, so when you add them together, you have to try to. So if it's negative, you know one would be positive and one would be negative. So you have to try to move this around in your head. I think it works better for me. Not sure, but for you. But once you master it, I think you could just really get quick. So as we replay the video multiple times, just practice. Let me give you another example. So let's say example 16x squared minus 17x plus. Then probably just 1. Okay. 1. Actually, negative 16 plus 17x minus 1. So again, what we have to do is put this down here, x and x, and then prime factorize these. So for 16, I just sort of ignore it first on the negative, but there's a 1, remember? So you have to remember there's a negative. Sorry, but so there's a negative. So what that would mean is either one of these. So actually you can sort of shift this a bit because maybe you don't think it works. So you might want to invent your own method or do anything you want, but you remember there's a negative. So either this is positive, this is negative, or this is positive and this is negative. But you can like sort of bend the system. This is not correct, but you can. For example, when I said it's positive, it has to be one of them positive, one of them negative. But you can sort of move the negative here because there's a negative. So 1, 1. So for example, this is negative. So move it here. You move it to here, and so this would be positive. It doesn't make sense. So it's a very flexible system. But also you have to be very careful for careless mistakes. So I myself don't want to move this around too much because it's very easy to get careless mistakes. However, you can do whatever you like but for this case, it works both ways because when as long as for this problem, because this is positive, correct? So as long as the negatives are diagonals to each other, is correct. So for example, if negative, negative, they're diagonals to each other. So sorry, yeah. So this would be a very good example of a negative. So what you would do next is also cross multiply. You don't have to write the arrows every single time. I'm just trying to express it. So again, you would have negative 16x times negative 1, which would be 16x. So you see, like I really like this system because it's really organized in a way that I really like appreciate the inventor of the design. So it would be 17x. So that would equal. So that's correct. So now we would have to group it. So as when you get faster, it's just really fast to understand this. So this is so now we covered factoring the trinomial. So the rest of this is mostly about memorizing the formula. I don't. You should memorize this instead of this because this is less helpful. Because perfect square trinomials, you can just use this with this method. And so grouping needs a bit of explanation. So for this problem, it's very well grouped. So first, we have to mess it up. So for example, 8x minus 5x plus 2x cubed minus 3. So the first thing you'll probably do is to turn to standard form. But if the question asks you to factor by grouping, you don't necessarily have to make it. But in this case, standard form would be correct. So you would reorganize it to commutative property of addition. And that's what I'm not commutative property. It's just moving things around. Because you're not moving not only numbers but also the positive negative. You understand? So this is standard form will also be so. What your group is, you try to have 2 or 3 or like just groups of equal groups. So however many numbers of groups you want, but each group has to contain the same number of terms as each other. So basically, in this example, 2 will be the number of each group. So you get what I'm trying to say. This is I have a bad habit of not writing the plus here. So actually you're supposed to write like this. So there's 2 terms here, 2 terms here. So there should be the same number of terms here. Because the point of factor by grouping is to have these 2 parentheses be the exact same. So we can factor it sort of by GCF. So 2x squared minus 5. Because this is this is sort of like a leading coefficient. So x plus 4. So there you go. This is factor by grouping, but this would be 2x minus x plus 4. So this is how you factor by grouping. But after you factor by grouping does not necessarily mean you're in factor. So I think we've covered most of factoring. Difference of squares, yeah, it's just mostly memorization. No, I think it's really easy. The only thing you have to memorize is probably this one. This one's sort of harder to memorize. So we should go over the examples. I think we went over difference of squares. Perfect square, yeah, we did that. So let's go over 2 cubes. Let's not use this problem. Let's use our own problem. So nice cube. 27. Let's just 8. It's more simpler than it's 27. So 1 no. Well, maybe I can do this. Or actually make this. So the formula is if it's a plus or minus b times a minus plus ab plus b. So what this means is if it's the top one is the example. If you're using the top one, example this is plus. So if you want to use the top one, then you'll use the top one all the way. For example, if you use plus, then the next one you'll have to use minus because it's both on the top. You understand? So it's sort of flipped over in a sense. I'll have to quickly go over this. So what's a? What's 8x cubed to the cubic root? So that would be 2x. This is plus 9. So here you go, and then you would factor with your method if it's factorable. Let's just do that. Factor so x. So for my purpose, I don't really want to prime factorize because I think it's. Let me think. This is. Oh, you can use a quadratic. No, this is not factorable. Yeah, this is not factorable. Yes, I'm pretty sure this is not factorable. Like this trinomial is not factorable. So anyways, now we have completed a problem of sum and difference of 2 cubes. So I think we covered factoring. so far. So in the next video we will cover possible zeros in this card. Oh, let me just mention other ways of finding the roots or the zeros of it. There's many different ways. Let me just write them. Other ways. Another way would be possible zeros, possible zeros, plus discards, plus dividing. That would be next video. In the second way, maybe plus factor, remainder theorem. I like it remainder theorem. I think both names. Confirm that. I'll go with factor theorem. Factor theorem. Be most of the next video. And if it's a quadratic, of course, the quadratic formula. There's all factors. So completing the square. And of course, you could guess and check, or sort of like graph. So these are sort of like, I won't X it out completely, but just unless you're required to, if you really can, the quadratic formula would be better. So the quadratic formula, I'm not sure if it's covered already, but yeah, I think it's covered. So I'm finished with the part 1 of the zeros of polynomials by factoring. So that's part 1. So next video, in case I've missed something, I'll just add it onto this video. So thank you for listening to my recording lesson of 3.4 zeros polynomials.